Hi everyone, today we're going to be talking about a concept which is quite difficult when beginning to learn about mathematical proofs, and that is quantifiers, more specifically negating those quantifiers. This can be quite confusing, but it is essential because so many mathematical statements have quantifiers as an essential part of them. And when we're proving mathematical statements, a lot of the times it makes our lives easier if we can also negate those statements. So negating quantifiers is a concept which we will use throughout our entire time learning about mathematical proofs and even other parts of mathematics. So let's begin by looking at an example here, which includes a universal quantifier. So this universal quantifier, we see it at the beginning here, denoted by this upside down A. So let's read the statement from left to right to get a feeling for what it's telling us. It says, for all integers n squared minus 3n is less than 0. So let's think about, do we think that this is true or do we think that this is false? Well, if we test out a few integers, let's say 1, for example, we have 1 squared minus 3 times 1, which is negative 2, which is strictly less than 0. If we test 2, we have 2 squared, which is 4 minus 3 times 2. 4 minus 6 is negative 2, which is also strictly less than 0. But let's see 3, for example. If we take this one step further, we have 3 squared minus 3 times 3, which is also 3 squared. So we have 3 squared minus 3 squared. Well, that gives us 0, which is not strictly less than 0. And then if we keep doing this further and further with increasing integers, we can see that this starts being constantly positive. So if we keep going with 4, 5, 6, we can see that the larger the numbers are, the larger the integers are, this actually remains positive, which is not strictly less than 0. So we have this feeling now that this statement is actually false. It only works for the first few integers that we tested, but with others, it doesn't seem to work. So we want to remind ourselves, and this is really important for all sorts of mathematical proofs, that if the negation is true, the original statement is false. So that's a concept that we use in proofs all the time. So if we have a statement that we have this feeling that it is in fact false, if we can prove that the negation is true, well then we've proved that the original statement is false, because the negation and the original statement cannot be true at the same time. If the original statement is true, then the negation is false, and if the original statement is false, then the negation is true. So now that we had this in our brainstorming session just now, we have this feeling that this statement is in fact false. So maybe we can negate it, and that'll give us something that we can actually prove to be true, which in turn will prove that the original statement is false. Let's write this down instead of just talking about it. So if we negate this statement, well, going from left to right, negating the universal quantifier would give us the existential quantifier. So negating for all integers n would give us there exists an integer n such that, and now we want to negate this here. We want to negate our predicate. And what that says is, in the original statement, n squared minus 3n is strictly less than 0. So negating that would be n squared minus 3n. I'll write it like this at first, is not strictly less than 0. But actually we can write this not strictly less than 0 as greater than or equal to 0 to make things a little bit more readable. So now let's read this from left to right. This is our negation now. Our negation says there exists an integer n such that n squared minus 3n is greater than or equal to 0. Well, now that we have this existential quantifier here, all that we have to do is find an example for which this works. And if we find an example for which this works, then we proved this statement to be true, which means that we've also proved the original statement to be false. Well, we want to find, does there exist some integer such that this applies? So n squared minus 3n is greater than or equal to 0. But actually, when we were brainstorming about whether this original statement is true or false, we did find an integer for which this will work. And that was 3. The first integer that we sort of had some issues with was 3. So we can see that if we apply 3 here, 3 squared minus 3 times 3, that gives us 0, which is in fact greater than or equal to 0. Okay, so the way that we can actually prove this to be true is we can say, okay, the negation is true. And why is it true? Well, we just have to find one example because we have this existential quantifier. All that it's asking us is, does there exist some n integer for which this works? Well, we can choose the integer 3. So we let n equal to 3. And now if we let n equal to 3, then we have n squared minus 3n is equal to 0, which is also greater than or equal to 0. So I'll put a check mark here showing that this in fact works. Of course, we can write this a little bit more formally, but essentially we have proved that this negation is true. And because we proved that the negation is true, we have proved that the original statement is false. Okay, so what are a few key takeaways we can take from this example? Well, the first one is that the negation of the universal quantifier is the existential quantifier and vice versa. We'll see an example later on where we negate the existential quantifier, but essentially whenever we have this universal, it becomes the existential in the negation, and when we have an existential, it becomes the universal in the negation. Okay, and another key takeaway from here is that the domain remains unchanged in a negated statement. What I mean by that is that we have this domain here. This domain tells us that n, our variable, is in the integers. And if we look at our negation, n is still in the integers. We didn't do this. This did not change. So our domain remains unchanged. And that is very essential for negating statements, especially statements with quantifiers. So we'll talk a little bit about why the domain remains unchanged and what would happen if we actually changed the domain. But before we do that, let's do another practice problem with universal quantifiers. So in this practice problem, I've colored certain parts just so that we can label the different parts of a statement and understand which parts remain unchanged in a negation and which parts do change in a negation. But before we do that, let's just read it from left to right so that we understand what this statement is saying. So the statement is saying for all natural numbers n squared plus 1 is a prime. Now, before we talk about whether we feel like this is true or false, let's label these parts of the statement. Well, on the left here in green, we have our quantifier. In this case, it is the universal quantifier, but it could also be the existential quantifier. That is our quantifier. It's saying for all n. And now in blue here, we have our domain. So n is our variable, and the domain tells us what set our variable belongs to. So we have this domain telling us that n is a natural number. It's part of the set of natural numbers. And now to the right, we have this larger part of our statement, which is our predicate. So our predicate is like the meat of the statement. Our predicate tells us what are we actually trying to prove as true or false. So now let's think about whether we feel like this is true or false. Well, let's see. Let's test out a few numbers and we can see if this is true or false. Let's say a natural number, let's say 2. If we test out 2, we have 2 squared plus 1. That gives us 5. 5 is a prime, so this works for 2. Let's test 3. Well, if we do 3 squared plus 1, that gives us 10, which actually isn't a prime. So we can see we already found a place where this doesn't work. And since this is a universal quantifier, then it has to work for all natural numbers. And we just found one for which it doesn't work, 3. So actually, this statement is false. We haven't quite properly proved it yet, but we know that it's false. We just need to prove it in a nice way. So the way that we can prove it is we can start by negating the statement and seeing if maybe instead of proving that the statement is false, we can prove that the negation is true. So from left to right, we would have The universal quantifier turns into the existential. So we have there exists a natural number n such that, and now we want to negate the predicate. Well, the negation of n squared plus 1 is a prime, is n squared plus 1 is not a prime. So n squared plus 1 is not a prime, is a negation of the predicate. So now reading the negation from left to right, we have there exists a natural number n such that n squared plus 1 is not a prime. Well, actually, we can just prove this because we have this existential quantifier here. We can just prove this by finding an example for which this works. And we did find that example when we were brainstorming this original statement, whether it was true or false. And that example was 3. So actually, the negation is true. And why is it true? Well, we can choose the natural number n to be 3. And if n is 3, then n squared plus 1 is equal to 10. But 10 is not a prime. So because 10 is not a prime, then this works. So the negation is true, which means that the original statement is false. Again, just to clarify that, the original statement is false because the negation is true. Okay, so now let's do some practice where our statement has an existential quantifier. Let's read it from left to right together. There exists an integer n such that 2n plus 3 over 2 is also an integer. Let's think about whether this statement seems to be true or false. Well, just on the side here, let's write this down. Actually, we can write 2n plus 3 over 2 as 2n over 2 plus 3 over 2. Well, 2n over 2 is just n, so we have n plus 3 over 2. 3 over 2 is not an integer, right? That's 1.5. But n is an integer. We have from the statement here, we know that n is an integer. Well, if we have any integer plus 3 over 2, meaning plus 1.5, we would end with a number which is not an integer. So actually, this statement seems to be false. It seems like this doesn't work. So because it seems to be false, let's negate it and let's see if that is something that we can prove to be true. Because if we prove the negation to be true, the original statement is false. Okay, so negating it from left to right, we have the existential quantifier, so we get the universal quantifier. In other words, for all integers n. And now we want to negate this predicate here. Well, the negation of 2n plus 3 over 2 is an integer, would be 2n plus 3 over 2 is not an integer. So here we would have is not part of the integers. Okay, so now how could we prove this? Well, we just talked about it a little while ago with our scratch work. We said that this in fact is true. And why is this true? Well, because 2n plus 3 over 2, we said it can be written as 2n over 2 plus 3 over 2, which is also can be written as n plus 3 over 2. But now, because n is an integer, so because n is an integer and 3 over 2 is not an integer, then n plus 3 over 2 will not be an integer. Of course, a proper proof would be maybe a little bit more words and a little bit more formal, but because we just proved that for all integers n, this is the case, we proved that the negation is true, meaning that the original statement is false. Okay, so now let's talk briefly about why this domain remains unchanged in negated statements. Because it's one thing to memorize that we should never negate the domain or that we should never change the domain, but it's another thing to understand why this works and what actually happens if we do change the domain in a negated statement. So here we have an example. We have for all natural numbers n cubed is greater than or equal to 0. Well, this is correct, right? Because we have all natural numbers, those are positive numbers, and whenever we cube a positive number, we have a number which is also positive. So this statement is true, right? All cubed natural numbers will be greater than or equal to 0. So if the original statement, if this statement is true, then the negation should be false. Well, let's take a look at one example where we negate this statement properly, and it should be false, and another example where we actually change the domain, so we negate it improperly. And let's see what happens. First of all, the proper negation would be, so instead of for all natural numbers n, we would have there exists a natural number n. The domain remains unchanged. So there exists a natural number n such that the negation of n cubed is greater than or equal to 0 would be n cubed is strictly less than 0. Well, this does seem false, right? Because any natural number that we take, if we cube it, it should be positive. It should be greater than or equal to 0. So this is false. We can't find any natural number where if we cube it, we get a negative number. That doesn't seem to make sense. But let's take a look at the wrong negation. So let's take a look at if we do not keep the domain the same. Well, if we do that, we would get, okay, the negation of the universal quantifier is the existential quantifier, but then we would also negate or change this domain. So we would have there exists an n which is not in the natural numbers, such that, and now we negate the predicate as well, just like we did before, n cubed is strictly less than 0. Well, let's think about this. There exists a number which is not a natural number such that n cubed is less than 0. Well, if we take any negative integer and if we cube it, we get back a negative integer, right? Let's take -1, for example. -1 is not a natural number, but if we cube it, we get -1 as well, which is strictly less than 0. So this statement is actually true. We found an example where it works. We found an n being -1, which is not part of the natural numbers, for which n cubed is strictly less than 0. So actually, this negated statement is true. But the negation should be false because the original statement was true. So something is wrong here. So that's why it is so important for us to keep our domain the same when negating statements, because that'll give us a proper negation. If we do change our domain like we did here, we can actually end up with a completely different statement, which gives us a completely different result. So for the next video, we'll go through some more complicated examples of negating quantifiers, some statements where we have both the universal and the existential quantifier in the same statement.